Hello there, how are you guys doing? We have covered basic concepts in current electricity, and in case you have not had a chance to look into it, it is put in the description below. Please go ahead and brush up those concepts. Today I'll be covering some numericals based on current electricity, starting with numericals around resistance and resistivity. So let's go. So we are going to discuss about resistivity and numericals associated with that in the first session of this. So if you look at it, the questions based on resistivity will be broadly be of three categories. The first category, the simplest one, is find the value of the resistance, and they will give us the resistivity, the length of the wire, and the area of cross section of the wire. And just to let you know that the formula for resistance R is equal to rho into L by A. Okay, so they'll simply say find R when they are giving you rho, L and A. That's the simplest of the numerical types that we can do. The second set of numericals that they will give us is to compare R. Okay, so they'll say, hey, you have taken a given length of wire and it has some cross section and its resistance is something. So you make the length 3 times and you make the area of cross section 3/4 of the earlier one. Find the new resistance. So that's what we are calling it as compare. But there they are giving you either the new length divided by the old length, or they're going to give you the ratio, and they're going to give us some data about the area of cross section. So that's the second type. And the third type is when they say that the wire is stretched. Okay, so they will give some resistance in the original length, and then they will say the wire is stretched to double the length or triple the length. Then find the new area, or find the ratio of the new resistance with respect to the old resistance. So that's the third type. We will do sample numericals for each of these types. So if you have studied the given problem, and if you try to capture the data that is given here, we see that the resistance of the wire is given. Resistance is given as 2 ohm, and that the length of the wire is given. The length of the wire is given as 15 centimeter, and the area of cross section is also given as 25 centimeters square. Given this, they are asking us to find out what is the specific resistance or what is the resistivity. So resistivity and specific resistance are one and the same. Okay, so as discussed, we will use the same formula. R is equal to rho L by A. Here we want to find rho, which means that rho is going to be R into A by L. Okay, so we kind of rearrange the things and we get this. Okay, so now one thing to be careful about is that length is given in centimeters, and resistivity we are going to calculate. The units of resistivity is going to be ohm meter. Therefore we have to convert both these units into SI units, meters. Okay, so therefore the length is going to be 15 by 100 or 0.15 centimeters, 0.15 meter, and area of cross section is 25 centimeters square. So we can say 25 into centimeter is 10 raised to minus 2 into 10 raised to minus 2, or 25 into 10 to the power of minus 4 meter square. So we have converted the length and area to SI units. All we need to do is simply plonk in the formula and say resistivity is equal to R given as 2. Area of cross section is 25 into 10 raised to minus 4, and the length has been given as 15 or 0.15. I will write it as 15 into 10 raised to minus 2. Instead of 0.15, we can always say 15 into 10 raised to minus 2. This, when it goes on top, will become plus 2. Overall, this is going to be 10 raised to minus 2. Then this is going to be 2 into 25 is, or I can cancel out 5 5s, 5 3s. So this is going to be 10 by 3. 10 by 3 into 10 to the power of minus 2 ohm meter. So 10 by 3 you can write it as 3.3. 3.3 into 10 to the power of minus 2 ohm meter is going to be our answer. I hope it is clear. So we'll now tackle the second type of numerical, which is the ratios of length is given and the ratios of area of cross section is given. We have to compute the resistances. Okay, so if you study the given numerical here, it's told that the length of the wire is doubled. Okay, so let's start documenting it. If you say L1 is the original length, okay, and the length is doubled, means L2 is going to become 2L1. Okay, you can say this is the original length and this is the new length. Okay, so this is 2L1, and it is given in the numerical that the area of cross section has become 1/3. Okay, so we will tell that initial area of cross section is A1. Now area of cross section has become 1/3, means it is going to be A1 by 3. Okay, and we are now supposed to find the ratio of the resistance. Okay, so let's say that initially the resistance was R1, and we are now supposed to find out what is going to be R2, and therefore we are supposed to compare R1 by R2. What is going to be R1 by R2? So this is what we need to find. Okay, so because the material of the wire has not been changed, okay, we take that, let that be rho, and we'll keep it constant both for the initial condition, the first condition and second condition. And then we will use the formula R. Okay, we will say R1 was rho into L1 by A1. Okay, these are all the initial set of conditions, first case. And then we will say R2 is going to be, resistivity is the same because the material has not been changed, rho into length. The second case, the new length has become 2L1, so we say 2L1, and area of cross section has become 1/3 of the first one, so we'll say A2 is nothing but A1 by 3. Okay, so we see that when we simplify, this becomes 2 times rho into L1 divided by A1, and this 3 in the denominator comes up on top into 3. 2 into 3 is nothing but 6. 6 times rho into L1 by A1. This is what is going to be R2. And if you look at what we had here, R1 is nothing but rho L1 by A1, right? Because area was A1. We can just substitute the whole thing here in this. So rho L1 by A1 is nothing but R1. So this becomes 6 times of R1. Okay, so if you want to compare the ratios, you want to find R1 by R2, we simply move R2 that side and say R1 divided by R2 is going to be equal to 1 by 6. Right, that means the resistance in the second case is going to be 6 times the resistance in the first case, or R1 by R2 is going to be 1 by 6. I hope you understood this. So let's discuss the third type, and this third type is about the wire being stretched. So if you look at the numerical here, it's saying that compare the resistance when the length of the wire has been increased by 3 times. Okay, so let's go ahead and put it. The wire is stretched by 3 times, so let L1 be the initial length. Okay, and this L2 is going to be 3 times. It is stretched by 3 times. L2 is 3L1, and let A1 be the initial area. The second time area is not given after it's stretched. Okay, so the difference between the length being increased and the length being stretched, okay, is like this. Here, when you're talking about the length of the wire being stretched, right, it is this wire which is actually pulled. So you're catching it by both ends and you're just stretching it. So when you stretch it, the area of cross section of the wire, or the diameter of the wire, is not going to remain the same. Okay, the wire is going to become thinner and it is going to increase in length. Okay, so this was L1, now this is 3L1. We can't take this as A1 and A1, right? This area is now going to change. So we have to find out how much this A1 is going, this area is going to be with respect to this. Okay. How do you do this? So we will use the concept that there is no loss in material, or the volume of the wire is going to be the same. Therefore, let's look at the volume in the first case. It is going to be L1 multiplied by A1, because this is like a cylinder, right? Area of the base into height will be the volume. So there is no loss of material, volume is the same, should be equal to the second case. In the second case, what has happened? This length has become 3L1. So this is 3L1, and we don't know what its area is going to be, so we're going to just say it as A2. So this is going to be 3L1 times A2. Then we'll see here, what is A2 now? A2 is nothing but L1 into A1 divided by 3L1, right? That means A2 is going to be 1/3 of A1. Okay, so it's a reciprocal relationship. So if you increase it by 3 times, the area is always going to become 1/3. If the length is becoming double, then the area is going to be half. If the length is quadrupling, then the area is going to be 1/4. So you can remember that the logic behind that is volume is going to remain the same. Okay, so with that you can come out with this inference. Now it becomes simple for us. What is going to be the resistance? The earlier resistance is R1 is rho into L1 by A1 as usual, and this R2 now is going to be rho into L1 is now become 3L1, and A2 is now going to be 1/3 of it. Okay, A1 by 3. So if this 3 will go on top, and this 3 is the 3 into 3 will become 9. 9 times of rho into L1 by A1, and rho L1 by A1 is nothing but R1. So this is going to be 9 times of R1. Okay, so this is R2. So the second time, the resistance in the second case, once you finished doing the stretching, is going to increase it 9-fold, right? So, or you can say R1 divided by R2 is nothing but 1 by 9, or R2 by R1 is going to be 9. I hope you have followed this. Before we go to the next part of the lesson, we need to discuss a bit about potential, right? And we have made a video about electricity basics in which potential is also covered, but in case you have not, a quick summary about it. If we have a charge here, and because of which you have an electric field, we said that within the electric field there can be a point here, and this point here will have a potential. Okay, and that potential we say is potential at A. Supposing we call this point as A, potential at A. What is the definition for that? We say that, yeah, this is where the electric field starts. So you try to get some charge from beyond the field. We'll call, let's say we are getting some Q charge, and it's a positive charge. Okay, and if you get it from beyond the field, and when this Q charge enters the field, right, it's entering the field, then because this is also a positive charge, this charge will feel repulsive force. It will experience repulsive force here. So if you want to get this charge to this point, then we have to apply a force on this charge and get it from outside the field to within this point here. Okay, so the charge Q is now going to reside here. Okay, so you are applying force here, external force you are putting, and you're traveling through some distance. That means you're doing the work. Okay, so when you say potential, what we are telling is how much work did we do, okay, and what is the charge that we got to that point. So W by Q, work done per charge, is the definition of potential. Okay, so if supposing we take another point, if we have another point here, let's say B, and if you want to get a similar charge from outside the field to this point B, we see that once this charge enters it, repulsive force is there, so you have to apply external force, apply it, get it here, But now we have done lesser amount of work because this is a different point. We didn't need to push the charge so far, isn't it? So the work done at point B is lesser, okay? So we say potential at point B is work done to get it till point B divided by Q. You can say this is still A, this is still B, okay? So in that way, different points within the electric field will have different potentials. I hope this is clear. We will talk about the important concept of potential difference or potential drop across various points within an electrical circuit. So to help us through the concept, I have drawn two diagrams out here, case A and case B, where we have taken a battery and we have assumed that one end of the battery positive terminal is at plus 10 volt and the other end we have kept it at 0. And if you look at the first case, there is no resistance within the circuit. So we have just taken a good conducting wire and connected the positive terminal along with the negative terminal or zero potential. Whereas in the case of case B, we have a circuit which has two resistances, R1 and R2, which are connected. The battery plus 10, 0 remains the same. So let's examine the concept of potential difference given these contexts. So this diagram I can explain by drawing this simplified version of it. This plus 10 is this point and this 0 is out here. We can call this as negative or we can call this as 0. So if I were to draw a potential graph here, then we will see that all points which are connected to this positive terminal, because there is no resistance here, all these points here will be at plus 10 volts itself. And when you come to this negative terminal which is here, suddenly the potential drops to 0. Okay, so if in fact this kind of a connection is not good because you are basically shorting the circuit, you are allowing the charges to discharge instantaneously. This is not good. Now let's come to the second diagram where we have this plus 10 and then we have drawn these two resistances which are there here, and from this point to this point there is no resistance, the potential remains the same. Right, it is indicated here by this point. So the potential, if we say this is plus 10, the potential here will remain 10. And then once you go across the resistance, so if you consider this point here, this we can call this as 1, we can call this as 2. At point 2, there is a difference in potential. So it could be some value here, let's say this is 5, right? Similarly, from 2 to, let's call this point as 3, there is no drop in potential. And from this here, if we call this point as 4, this point is connected to 0 potential, so this is going to be 0. Point 4, the potential is going to be 0. So in this way, if you want to measure the potential difference between 1 and 2, that potential difference will be here at point 1, the potential is 10, at point 2, the potential is 5. So if you put a voltmeter and measure it, this will show 10 minus 5 volts here. 10 minus 5, potential difference will be 5 volts. If you connect a voltmeter here across this resistance, it will say the entire thing till here is 10 volts. Point 2 is 5, 10 minus 5, this will read 5 volt. And from here between 2 and 3, the potential is 5 volt here, right across all these things. And then suddenly here the potential at the point 4 is 0. Therefore here if you would connect to a voltmeter, this is going to measure once again 5 minus 0, this will measure 5. Okay, so this is what is called measuring the potential difference between the points, the different points within a circuit. There will be no potential drop if there is no resistance, as we saw in this case, but the minute we have a resistance, there is going to be a potential drop which can be measured by connecting a voltmeter in parallel between those points. So let's now talk about resistances which are connected in a specific way called resistances in series. For example, we have taken two resistances out here and connected them in this fashion. This resistance is connected with this resistance in series. Basically, they will be one behind the other. This is called the series arrangement. Okay, so we would like to use the concept that we have studied in the last class, where we said that whatever be the potential difference that is there across the battery, right, across the source, that gets dropped across the resistances which are available in the circuit, right? So what we are essentially saying is V, the potential difference across the battery, is equal to V1 plus V2. V1 plus V2. If we have one more resistance out here and we call it R3, then there will be a potential difference across that resistance, and we will say V is equal to V1 plus V2 plus V3. The crux of it is this potential is this potential is dropped across all the resistances. So for computing the current that flows through the circuit and for computing the potential drop, we need to come up with a way where we can simplify. If we have so many resistances across which are connected in series, can we replace them with a single resistance which fulfills the purpose of all these three guys which are connected in series. So we want to see if it is possible to collapse these guys as one single resistance, which we are calling it as R effective. So the circuit would simply look like this. Whatever battery is there, we connect it to R effective. So this and this will be equivalent. How do we do that? So we will go with this concept, V is equal to V1 plus V2 plus V3. And then we will examine what will this V1 be. Okay, if we assume that the current I is passing through this circuit, then this I is going to go through R1, and the same I is going to go through R2 and R3 as well. In fact, that is one other way of identifying a series circuit, because the current that is flowing through the resistances will be the same. So that being the case, this potential drop V1 is nothing but I into R1. This is nothing but I into R1. This potential drop V2 is nothing but I into R2. We are using the Ohm's law, V is equal to IR. And this potential drop is nothing but I into R3. So if you use the concept V is equal to V1 plus V2 plus V3, we can say V is nothing but I into R, or R effective, because we are considering that all these three resistances is collapsed together and made into a R effective. So in this circuit, V will be nothing but I into R effective will be equal to V1. V1 is nothing but IR1 plus V2 is nothing but IR2 and IR3. I is remaining the same, so we can take I common and knock it off and get the equation R effective is equal to R1 plus R2 plus R3. So this is a very handy formula for handling resistances which are connected in series. So we could quickly collapse them and have a simplified version of the circuit and go ahead computing the current or the voltage drop across the various points. Now let's talk about resistances which are connected in this kind of an arrangement, which is called resistance in parallel. And like we did for series, we want to come up with a simplified resistance, R effective resistance, which will help us to club resistances which are connected in parallel. So one thing that we must know before we go ahead is, see, this is like let's say this is having a potential V. We know that there is no resistance here, so this point also is at V. And this point is, let's assume 0. That means the potential difference here is V. So this point is also at, this point is at 0. This point is at V. So if we were to connect a voltmeter between these 2 points, the voltmeter is going to measure V. Whatever is the voltage drop here, the voltmeter is going to measure this. Now let's examine this, which we can call limb 1 or arm 1 or whatever. And this is our limb 2 or arm 2. So this, there is no resistance from here till here. That means this point is also at V and this point is at 0. So if you connect a voltmeter here, that too will read V. Likewise, if you connect a voltmeter here, that too will read V. So to sum it up, if you are having a parallel block, the potential drop of the parallel block is going to be the same as the potential drop that is happening within each limb in the parallel block. V is going to be the same. Point number 1. Now let's look at current. So supposing with all this, there is a current I that is flowing through the circuit. Right? So the I comes out here, it sees two paths for it to flow. It may, I1 will go through this, I2 may go through the second limb. So the current need not split as the same. It depends on what is the resistance we have connected in the path. If you have a higher resistance, lower current will flow. If you have a lower resistance, higher current will flow, inversely proportional to each other. So we can use the condition that in a parallel circuit, I is going to be I1 plus I2, because once this I merges here, I1, this is I2, so you get back I is I out here, I1 plus I2, or once again I is flowing in this circuit. Okay, so the condition we will use is I is equal to I1 plus I2. But then if you look at Ohm's law and say V is equal to IR, what is I? I is nothing but V by R. So if we say that this entire thing can be clubbed as one effective resistance, which we are calling it as R effective, because that's what is our purpose. We want to simplify resistances in a block as a single resistance, right? So as far as the entire circuit is concerned, we can say V is equal to I into R effective. So here this I will be V divided by R effective, right? So we can say this is V divided by R effective is equal to I1. What will I1 be? The potential drop across this is V and this is R1. So this will be V divided by R1. And as you might have guessed, I2 is going to be V divided by R2. To simplify this, we can take V common on both left hand side, right hand side, cancel that out and end up with 1 by R effective is equal to 1 by R1 plus 1 by R2, which is the equation we will be using in order to simplify whenever we have pieces of circuit which are connected in parallel. Let's take a quick recall and recollect what we have learnt in the last couple of clips. The first thing we have learnt is about the definition of potential. We've seen what we mean by potential drop, how potential is dropping across a resistance. Then we've understood that we can connect resistances in series and in parallel, and how we could simplify a group of resistances in series and parallel by using the formula, respective formula for R effective. So using these concepts, let's solve some numericals in current electricity. So let's take this circuit and we will use the concepts that we've learnt and try to simplify it. So we will say, let's find the effective resistance for the entire circuit, and let's find current. Let's keep that as the goal, and we'll give some values. Let this be 6 volts battery, and let this be some 1.6 ohms. Let this be 4 ohm, and let this be 6 ohm. So these are the values which we've given ourselves. And so we immediately identified that this particular block that we have, constitutes a parallel block. So we can use the formula for R effective, 1 by R effective is equal to 1 by R1 plus 1 by R2 to simplify this particular block. So what will that become? That will become 1 by 4 plus 1 by 6. So you can say for the parallel block R effective is this, LCM will be 12, 4 3s plus 2, or it is 5 by 12, or R effective is going to be the reciprocal of that, or 12 by 5. 12 by 5 is 5 2 is 10, 2.4. So the entire thing can be replaced by a resistance which is 2.4 ohm. That resultant simplified circuit, because we are saying that the entire thing is to simplify the circuit. So we have 1.6 out here, and both of these have collapsed to a 2.4 ohm resistance, and then we have the 6-volt battery. Now we see that this 1.6 and 2 ohm resistances are in series. So we use the formula for the series block. Series block is nothing but R effective is R1 plus R2. So R1 plus R2 is 1.6. We will write it down. R effective is R1 plus R2, which is 1.6 plus 2.4. 1 plus 2 is 3, 3 plus 1 is 4 ohms. So that means to find out the current in the circuit, let's draw the simplified diagram. So we have the 6 volts battery. Overall R effective we have found out to be 4 ohms, I think. 4 ohms, R effective is 4 ohms. We simply use Ohm's law, V is equal to IR, and say I has to be equal to V by R, which is 6 by 4 or 1.5 ampere. So calculating I has become very easy because we use the formulae for handling the resistances in parallel, resistance in series, and coming out with the overall effective resistance, and then simply using Ohm's law in order to find the current which flows through the circuit. I hope you followed this. Let's try our hand at this numerical, where we have been given a series of resistances connected in this fashion, and we are told find the effective resistance of this circuit, find the R effective, and between the points X and Y. Okay, so how we have, between which points is important, between X and Y. So we see, to do these kind of numericals, we have to identify which of the resistances are in series and parallel. To do that, let's look at it. Let's current come through this. We see that here current is going to split. Let's call this I, and this is going to be I1, and let's say this is I2. So this looks like is constituting one branch, because whatever current flows through this will also flow through this. Okay, that means this resistance and this resistance, because the same current is flowing through them, are in series. So 2 ohms, these two are in series. And then when you look at this current I2 flowing through this branch, I2 is also flowing through this resistance. So we can assume that these two are once again in series. Okay, so applying the formula for effective resistance in series, we get these two put together, 2 plus 2 is 4 ohms. So the circuit can be simplified in this way. 2 plus 2 is 4 ohms, and here too 2 plus 2 is 4 ohms, with the current I1 passing through this and I2 passing through this. And then we see that these two guys are now in parallel. This is a point X and Y, and in parallel combination we can use the formula 1 by R effective is 1 by 4 plus 1 by 4, which makes it 2 by 4 or half. Therefore R effective is going to be 2 ohms. That means the entire block of resistances between point X and Y the effective resistance is going to be 2 ohms. I hope you followed this. So when you look at this numerical, we see that it's similar to the one we have done previously, but a word of caution, just look at the various points between which we are supposed to find the effective resistance. It's been changed. The earlier one we took X and Y, now we are taking X and Y here. This is the entry point, this is the exit point. So if you look at current flowing through this, once again we break it into two branches, I1 and I2. And we see that this I1 is now passing through this resistance, as well as this resistance, which makes all these three fellows be in series. So the effective resistance of all these guys will be R effective. We use the series formula 2 plus 2 plus 2, which becomes 6. And then in this limb I2, we have only one 2 ohm resistor. So the effective diagram now becomes 6 ohms and 2 ohms between the points X and Y. So we quickly see that this is a parallel block. Therefore, we have to use 1 by R effective is equal to 1 by R1 plus R2. And we get that 1 by R effective is equal to 4 by 6, or R effective now becomes 3 by 2 or 1.5 ohm. Okay, so let's not be just taken with the shape. We have to see what are the 2 points, entry and exit points, for us to calculate the R effective. So I hope you have followed this.